Hello everybody, I'm Akriti Kutyala and welcome back to my channel. We are starting a new series on RCC design, reinforced cement concrete, where you will not only learn about the manual design process, but also how to model it in Revit. This series is in collaboration with Novatr, a leading platform that helps civil engineers upgrade their skills with industry-focused courses on BIM, Revit, and more. Through this series, you'll gain both theoretical knowledge and practical expertise to excel in the field. So stay tuned, it's going to be an exciting journey.
In today's lecture, we'll be looking at another numerical on reinforced cement concrete using limit state method. We were discussing the topic design of beams. This is the fifth lecture in the series. So the prerequisites for the subject are IS 456-2000. I hope you have the copy handy so that you can refer to the code. On this channel, we have a few membership plans called the Himalayan Birch, which will cover the subjects fluid mechanics and surveying, and the Himalayan Oak, which will cover the subjects fluid mechanics, surveying, as well as steel structure design and drawing. So hope to see you in the membership plan. A quick review, we have covered 4 numerical problems. This is the 5th numerical problem, which we are going to cover on RCC beams. We've covered 3 numericals on simply supported beam and 1 on cantilever beam. We've covered tension bars, cutoff, and side face reinforcement. In this lecture, we'll be looking at the question we covered in the 3rd lecture, that is on simply supported beams with side face reinforcement. This was a deep beam and we had provided side face reinforcement. So in the same numerical, what we are going to do is we are going to provide bent up bars. In the previous numerical, we did not cover this part, and in this question, we'll be doing that. So let's go through the question very quickly. It says that design a simply supported beam with the following data. The clear span of the beam is 6 meters, superimposed dead load is 28 kilonewton per meter, live load is 28 kilonewton per meter. We have to use M20 concrete and Fe415 steel. The nominal cover which has been given to us is 20 mm and the bearing on walls is 800 mm. So in addition to all this, we have been clearly specified that we have to provide bent up bars. So the initial part of the question will be same and I'll be rushing through it because we've covered it in the previous lecture, that is the 3rd lecture of this series on RCC beams. So writing the given statements, live load is 25 kilonewton per meter, we can convert it to 25,000 Newton per meter, superimposed load 28 kilonewton per meter, which can be equated to 28,000 Newton per meter. Clear span is 6 meters, so this gets equal to 6,000 millimeter. Concrete is M20, which means that FCK will be 20 Newton per millimeter square. Fe given to us, the steel is 415 steel, Fe415. So Fy will be equal to 415 Newton per millimeter square. The nominal cover is 20 millimeter and we are assuming for the initial part the effective cover to be equal to 50 millimeters. This we have assumed. And one more thing is that we have to provide bent up bars. This will come to when the case arises. So dimensions of the beam, again like the previous question, we have L given us to be equal to 6,000 millimeters. So we are assuming D as L by 10 to L by 8. So that is 6,000 by 10 to 6,000 by 8, which comes between 600 mm to 750 mm. And we'll be assuming like previous case, D is equal to 650 mm. Then assuming B as D by 2 to 2 by 3D, which is 650 by 2 to 2 by 3 650, which is 325 millimeters to 433 millimeters, and thus we are assuming a value in between this given range or this calculated range, and we assume B is equal to 350 mm. So like in the previous slide, we had assumed the effective cover to be equal to 50 mm. So small d, the value of effective depth, can be calculated as equal to overall depth minus the effective cover, which is equal to 650 minus 50, that is 600 mm. Now effective span, the width of the support given to us in the question is 800 mm. So from clause 22.2 we can see for simply supported beam or slab, the effective span shall be integrally, not built integrally with its support, shall be taken as clear span plus the effective depth of the slab or beam, or center to center of the supports, whichever is less. So we have two cases from clause 22.2, that is center to center distance between the supports, which is clear span, plus half the support on the left side and half the support on the right side. And the other case is clear span plus effective depth. So we'll check both these cases. So for the first case, it calculates to be equal to 6.8 meters, and for the second case, it calculates to be equal to 6.6 meters. So as the code says that we have to take the lesser value, whichever is less. So the lower value out of the two is 6.6 meters. So we'll take the effective length to be equal to 6.6 meters. Now moving on to the self weight of the beam. Step 3. Self weight, we know that we calculate self weight using the overall depth of the beam, the width of the beam. We assume the length to be equal to 1 meter and the gamma RCC, or simply the unit weight of concrete, which can be calculated from clause 19.2.1, which says that for RCC, the value of gamma, or the unit weight, is equal to 25 kilonewton per meter cube. So 25 kilonewton per meter cube can be written as 25,000 newton per meter cube. We are converting it into a newton because everything else has been converted into newton per meter if we see the factored load in the next step. So this gets easier for us. So substituting the values, one thing we have to keep in mind is that the depth of the beam, the width of the beam, which we have assumed is in millimeters. So because we are assuming, or we are taking the value of gamma, the unit weight, in newton per meter, so we have to change these units as well into meters. So to do that, we have divided 650 by 1000 because now this becomes meter. Similarly, 350 by 1000 because this is meters. We have assumed the length of the beam to be equal to 1 meter and the unit weight in the units newton per meter cube. So now all the values are in meters, and this calculates to be equal to 5687.5 newton per meter. So this is the self weight of the beam which we have just assumed according to its dimensions. So moving on to step 4, the factored load. Live load is given to us as 25 kilonewton per meter. We've converted it into 25,000 newton per meter. Similarly, superimposed dead load is 28,000 newton per meter. Self weight is calculated equal to 5688 newton per meter. We know that the factored unit weight, the factored load, or UDL, will be equal to 1.5 times the sum of dead load plus live load. So dead load is equal to 28,000 plus 5,688. That is self weight plus the superimposed dead load. That is the total dead load, and live load is 25,000. So this calculates to be equal to 88,032 newton per meter. So this is the UDL, factored UDL, which will be acting on the beam. Now the next step will simply be calculating the ultimate maximum bending moment which acts. So we know that this is a simply supported beam on which a UDL of 88,032 Newton per meter is being imposed. So we can simply use the formula WUL effective square upon 8, WUL square by 8. So substituting these values, L effective we had calculated in the previous slides and was equal to 6.6 meters. So calculating, we get the ultimate maximum bending moment equal to 479.3 into 10 to the power 6 kilonewton millimeter. So we have to keep in mind that this value when we calculated was in Newton meter. However, this is a very large value, and what we can do is we can simply convert it into 10 to the power 6 by converting it into kilonewton millimeter for ease. So from previous questions, we also know that whenever we design a beam, we always design it to be a balanced section. So for the balanced section, mu, this maximum bending moment which we have calculated should be equal to mu limiting. So from this balance section, what we can do is we can simply refer to annexure G of the code and calculate the value of mu limiting. However, we use this as a check to calculate the D, check for D, that whether the D which we have provided or assumed in the previous slides, is it sufficient or not. So we use the formula given in annexure G, mu limiting is equal to 0.36 xu max by D into 1 minus 0.42 xu max by D, Bd square Fc K. So xu max can be simply calculated from clause 38.1. For Fe415, the value of xu max by D is equal to 0.48. So we substitute this value here and we get a short formula, that is 0.138 FCK BD square. Now from this, we know that mu limiting is equal to mu, and mu we've calculated in the previous slide to be equal to 479.3 into 10 to the power 6 kilonewton millimeters. So what we can do is we can check this value for D and calculate the value of D required as per the given load acting on the beam. So when we calculate this value, the required value of D calculates to be equal to 704.4 millimeters. However, what we have provided is very less, that is equal to 600 millimeters. So this is not okay and we will have to redesign. This is up to this point, it is completely same as what we had done in the lecture C of this series. So you can go there and look at a detailed video of that. So now we are going to redesign again and go move back to step 1. Dimensions of the beam are 800. The required D is 704. So since earlier we had assumed the dimension to be equal to 650, which was not sufficient. So the overall depth was not sufficient. So now what we have done is we have increased the value. How did we increase the value? The required value was 704 mm as per the previous slide. However, what we will do is we will take this value into consideration, increase it by some amount, and then recalculate or reverse the calculation. So now what I have done is I have assumed the value of D is equal to 750 mm, which is greater than the required value. So I'm just being safe. I can also assume the value to be 720 or 710 mm, but I don't want to keep on calculating or redesigning my beam again and again. So I have taken a margin of approximately 46 mm and assume the value of effective depth equal to 750 mm, and then simply add 50 mm effective cover. This is a rough calculation. So 50 mm effective cover, so this gives me capital D is equal to 800 mm. So I can simply write that the dimensions, the new dimensions of the beam are overall depth is 800 mm, effective depth is 750 mm, and the width we are not changing it and is equal to 350 mm as calculated in the previous part of the question. So step 2 is effective span. Now since we have changed the value of D, obviously this calculation will change slightly. So again referring to clause 22.2a, it can be clear span plus the width of the support on the left and the right side, half the width of the support on the left and the right side. So this calculates again to be equal to 6.8 meters. And the second part is clear span plus D, which will be 6000 plus 750 mm. This is the new value of D, which we've substituted. So 6.75 meters. So L effective will be equal to 6.75 meters, because we are again going with the least value or the lower value, 6.8 and 6.75. So the lower value is 6.75. This is the L effective value. Now again, using the same concept, we'll be calculating the self weight of the beam, substituting the new values, converting it into meters. We get the self weight to be equal to 7000 Newton per meter. We are factorizing this load. Dead load will be a sum of the superimposed dead load and self weight, and live load will be equal to 25,000 Newton per meter. So factorizing this with a value of 1.5, we get a UDL of 9000 Newton per meter, factored UDL of 9000 Newton per meter. Again, calculating the ultimate bending moment using the formula WU L effective squared by 8, substituting the new values of WU and L effective, we get the value of ultimate bending moment equal to 512.6 into 10 to the power 6 Newton millimeter. So this again, calculating it as a balance section or designing it as a balance section, we have mu is equal to mu limiting, again from annexure G, and from this formula substituting the value of xu max by d for Fe415 equal to 0.48, we get the formula 0.138 FCK BD square. Rechecking the value of d required, so d required from this formula calculates to be equal to 728 mm this time. However, we are safe this time because we had assumed a value of d greater than the previous value, and we had assumed it to be 750 mm. This is greater than 728 mm, which is the required value, hence we are safe. That is why initially, to just avoid failing here at this step again, I had assumed a greater value of small d. Now the new dimensions of the beam are: overall depth is 800 mm, the effective depth is 750 mm, and the width is 350 mm. So this is also same as the previous question. Now moving forward to step 6, where we calculate the area of tension steel. Area of tension steel can again be calculated using the formula provided in annexure G, which says that xu by d should be equal to 0.87 F by AST upon 0.36 FCK BD. So from here we can calculate the value of AST corresponding to maximum value of xu by d. And again, xu by d, xu max by d can be calculated from clause 38.1 for Fe415, which will be equal to 0.48. So substituting these values, we obtain a required value of area of tension steel is equal to 2512.67 millimeter square. Now to cover this required area of steel, we have to convert it into number of bars. So assuming 25 mm diameter bars initially, if we calculate, the number of bars required will be 5.11, and we will round it up to 6 bars, because the difference between 5.11 and 6 bars is a lot, and we are providing a lot of steel, wasting a lot of steel, and it matters economically when we are designing large structures. So we will have to recalculate this distribution. So trying 4 bars of 25 mm diameter and 2 bars of 20 mm diameter, and let's see where the sum of this total reinforcement falls. So this equates to 2591.79 millimeter square. So this value is greater than the required value. We require 2512 millimeter square, and we are providing 2591 millimeter square. So we have provided an extra value of around 70 millimeter square, which is sufficiently fine. So this is AST provided, and this is AST required, which we'll require in the next steps as well. So now we have provided an AST of 2591.79 millimeter square in the form of 4 25 mm diameter bars and 2 20 mm diameter bars. So we will check this for minimum and maximum steel specified by the code. So clause 26.5.1.1 says that the tension steel should be the AST upon BD should be equal to 0.85 upon Fi. This is the minimum value. So if you see the minimum reinforcement required, so we can calculate the value of minimum steel that is given to us by the code. So this AST minimum will be calculated to be equal to 537.65 millimeters square, which is less than the AST provided. So we are safe here. Now moving on to the next clause, next part of the same clause, maximum reinforcement. It should not exceed 0.04 BD. So let's calculate this value. When we substitute B and D into the formula, we obtain 11,200 mm square, which is much greater than the AST provided of around 2600 millimeter square. So we can simply say that AST minimum is less than the AST provided and AST maximum is more than the AST provided. So we fall within the range and is safe. So now the question arises of the spacing between these bars. So how to calculate the spacing that is shaded with red? If you see, what I have done is I have provided the 25 mm diameter bars with green and the 20 mm diameter bars with red, purple here. And the spacing, clear spacing between the two bars is marked in maroon, if you can see here. So we have to calculate this spacing and check it with clause 26.3.2 if it satisfies the minimum spacing or not. So how can we do that? Using this clause, we can simply say that B is the total width of the beam. Then we have to subtract the effective depth, effective nominal cover, effective cover on both the sides, I'm sorry. And then how many bars are there that are to be subtracted? For 25 mm diameter bars, 1, 2, half of this bar and half of this bar. So that calculates to be equal to 3 bars. And then we also have to subtract these two 20 mm diameter bars completely. And how many spaces are there? If we see, this is 1, 2, 3, 4 and 5. So we will divide this horizontal space into 5 sections and calculate it as to be equal to 27 millimeter. So according to the clause, the diameter of how can you say that this minimum distance is safe or not? So it should be greater than the maximum diameter of the bar. The maximum diameter is 25 mm, so it is safe here. Aggregate size, we assume it to be around 20 mm, and we have to add 5 mm to it. So this calculates to be equal to 25 mm. However, in this case, we are slightly safe. 27 mm is slightly greater than 25 mm. And for the exam, if we are running out of time, we can completely say that this is safe and move on with our calculations. However, for practical purposes, this margin is very less, so we should be providing the bars in two layers of 25 mm diameter bars, one layer of 25 mm diameter bars and one layer of 20 mm diameter bars, and calculate the space again. So because we are providing the bars in two layers, we also have to provide a spacer bar now, so that these bars don't get entangled, or the space between these bars is sufficiently provided and they can develop a bond strength with the concrete. So this spacer bar is of 25 mm diameter and is provided at 1 meter center to center. So if we see a plan of this is the beam. The green bars are the 25 mm diameter bars. The purple ones are the 20 mm diameter bars. And the yellow ones are the spacer bars, which are placed at a distance of 1 meter center to center. So from the center of this bar to the center of this bar, the distance is equal to 1 meter. Similarly, from this bar to this bar, the distance is equal to 1 meter. So this is how the spacer bars are provided. Now, we have to keep in mind that because we are providing these bars in two different layers, the effective depth will be changed for this overall beam. Now, we also know that the required effective depth from the calculation is equal to 728 mm. So, the effective depth which we assume or we calculate now should not be less than 728 mm. So, what we are doing is we are providing an effective depth of 730 mm up to the center of the spacer bar. Now, because the effective depth up till the center of the spacer bar is 730 mm and the overall depth is 800 mm, so now the effective cover will be equal to 70 mm in this direction. So we can keep the effective cover in this direction equal to 50 mm for now, and we do not need to change that because the width has not been changed, and it will not cause a problem here. So again, B is the width of the beam. We subtract two effective covers from each side, and the number of bars left are 1, 2, half of this bar and half of this bar. So 3, 5 max, because this is the main bar which will, this is the main row which will be required to be checked for the minimum horizontal distance. There are just 2 bars here and can be spaced sufficiently apart. So number of spaces are 1, 2 and 3. So divided by 3 we get a value of 58.3 millimeters, which means that we are sufficiently safe because the diameter of bar is 25 mm and maximum diameter is 25 mm, and with aggregate coarse aggregate equal to 20 mm plus 5 mm also we get a value of 25 mm. So this is greater than 25 mm, hence it is safe. So we can move forward with this comfortably. So up till here the question was exactly same as what we had done in the third lecture of the series, RCC 1C. Therefore I have rushed it and I have revised it quickly. Now what we can do is, after this stage in the previous question we had designed vertical stirrups for the beam. However, in this question, what we'll be doing is we'll be providing or we'll be looking at our option of bent up bars as well. So from here, we'll be solving this question. What we can do is we can either cut off the bars, or we can bent up the bars, or we can, like the previous case, we can simply provide vertical stirrups. So we have seen sufficient examples of cutoff bars in simply supported beam and in cantilever. We have provided vertical stirrups in the third lecture of this series. However, we have not seen how do we provide bent up bars. So we'll be exploring this option in this particular question. Moreover, the question explicitly mentions that we have to provide bent up bars in this particular beam. So moving on, we can see clause 26.2.3.3, and it says that at least 1/3 of the positive moment reinforcement in a member shall extend along the same face of the member into the support to a length equal to LD by 3. So the minimum reinforcement which we can bend up should not be less, should not cause less than 1/3 of the reinforcement to enter the support. So this simply means that AST, that minimum AST that should enter the support, should be 1/3 of the AST provided. AST provided is equal to 2591.79 millimeters square. So AST minimum entering the support, here I can say support. So this calculates to be equal to 863.93 mm square. So the minimum reinforcement which should enter the support is 863.93 millimeter square. Now converting it into bars of 25 mm diameter, I can simply say that this is 863.93 divided by pi by 4 into 25 square. This calculates to be equal to 1.75 bars. So minimum of 2 bars, because we cannot provide 1.75 bars, so minimum of 2 bars of 25 mm diameter have to be extended into the support. So this is the minimum requirement. However, what we are going to do is we are going to provide only two 20 mm diameter bars to be bent up, and rest all the four 25 mm diameter bars to enter into the support. So assuming that the bars are to be bent up at section XX, X distance from the support, center of the support, and this is the theoretical bent up point. Now the challenge is to obtain this value of X. So for that we know that this is a simply supported beam with a UDL of 88,032 Newton per meter acting on it. We can calculate the value of reactions. So let's do that. This calculates to be equal to 297.108 kilonewton. Now calculating the factored bending moment at xx, how we can do is we can calculate the moments acting at x from this side. So r into x minus wu into x. So this will be the simple formula. I'm sorry, wu x square by 2 because w is a udl here. So the force will be wu acting into x, and this will be acting at the center of x. So wu x into x by 2. So we get this formula substituting the values we obtain, which gives us an equation 297,108x minus 44016 x squared. This bending moment at point xx, the theoretical bent up point, should be equal to the value of bending moment obtained from this formula given in annexure G, where the value of AST will be equal to AST1, that is the steel that is remaining. Now AST1 is the steel that is remaining or entering into the support beyond this point xx, which is equal to 425 mm diameter bars. So when we calculate this, we get 4 into 5 by 4 into 25 square, which gives us 1963.495 millimeters square. That is, these are the bars which are extended beyond the bent up section of xx. So 4 bars of 25 mm are being extended in this direction. So substituting the values in this formula, we obtain the bending moment the moment of resistance equal to 434988.12 into 10 to the power 3 Newton millimeter, which can be written as 434988 Newton meter. Now this moment of resistance should be equal to the bending moment acting at point xx, because this moment of resistance is also at point xx. We can equate these values and obtain a quadratic equation, and this quadratic equation can be solved for x, and we obtain the value of x1 is equal to 4.6022 and x2 is equal to 2.1477 meters. Now this simply means the two values, that one value of 4, if we take this as the reference line, we are obtaining a value of bend up of 2.15 approximately from this reference line, 2.15 meters, x2 is equal to this much, and the other value of 4.6, approximately 4.6 meters, is equal to this much. So we will be bending up the bars at both the ends, one from the left end and one from the right end. That's why we have these two values of 2.15 and 4.6. For our numerical purpose, we will be considering this value of 2.1477, which can be rounded up to 2.15 for simplicity. So this is the value from the from the center of the support. We can calculate this value from the center of this beam. So from the center of the beam, the value will be equal to 6.75 by 2 minus 2.15. So this calculates to be equal to 1.23 meters from the center of the beam. So this is the theoretical cutoff point. However, we know that this cannot be the actual cutoff point. We have to provide some development length. So that development length can be equal to 12 phi or d, whichever is the total value, whichever is greater. So substituting these values, 1.23 plus 12 phi. 12 phi here will be of the bar which is being bent up. So that is 20 mm diameter bar, which is equal to 2.40. I'm sorry, this will be divided by 1000 because 20 is in mm and this is in meters. So we have to convert this entire thing into meters. So this calculates to be equal to 1.23 plus 0.24 meters. This sums to be 1.47 from the center of the beam. Now the next part is 1.23 plus D. So 1.23 plus 730 divided by 1000. Again we have 730 is in mm and we have to convert it into meters. So this sums to be equal to 1.96 meters from the center of the beam. We have to take the greater value. So 1.96 mm is the greater value. So the actual cutoff point will be 1.96 meters from the center of the beam. I'm sorry, I'm repeatedly saying cutoff point, but this is the bent up point. So the actual bent up point from the center of the beam is equal to 1.96 meters. The next step is to calculate the shear for the beam. Now we know from previous questions and from clause 22.6.2 that the critical section for shear in a simply supported beam is at a distance d from the face of the support. So from the face of the support we move a distance equal to effective depth and we obtain this critical section of xx. So we need to calculate the factored shear force at the center of the support. So factored shear force at the center of the support will be equal to R, or we can simply say VU R. So WU L effective by 2. WU is 88,032 Newton per meter and L effective is 6.75 meters. So VU R will be equal to 297,108 Newton, that is equal to the reaction which we had calculated earlier. Now we need to calculate this distance x from the center of the beam at which this critical section lies. So to calculate this point, we simply have this value is half of the effective depth, that is 6 or the effective span. 6.75 divided by 2, half of effective depth span, sorry. Then half of the width of the support will be deducted and this effective depth d will be deducted to obtain this point xx or x from the center of the support. So this calculates to be equal to 2245 millimeters from the center. We have to keep in mind that we have to convert the L effective from meters into millimeters, that is 6750, because all the other values are in millimeters. So this is the value of x from the center of the support. Now we can simply write this in terms of meters. This is in millimeters, so this can be written as 2.25 meters from the center of the support. We have just rounded it up to 2.25 meters. Slight rounding up has been done here. Now the challenge is to obtain the shear force at this section XX, the critical section for shear. So from these triangles ABO and CDO, we know that these triangles are similar. We can calculate the value of CD or simply BUC. So substituting the values, now because we have taken x in meters, then we'll take L effective also in meters. So calculating VUC equal to 198072 Newton. So we have obtained the value of shear force at the critical section. Now from clause 40.1, we can calculate the nominal shear stress. So the nominal shear stress will be equal to VUC upon BD. So substituting these values, we obtain the nominal shear stress tau V is equal to 0.775 Newton per millimeter square. So from table 20, we can see that for M20, the maximum value of shear stress in concrete, that is tau C max, is equal to 2.8. So this value is less than tau C max of 2.8 Newton per mm square, hence it is safe. If this value was more, then we had to redesign. So this is okay. Now moving on, we have to calculate the shear stress resisted by concrete, that is tau C. So for that we will be referring to table 19, design shear strength of concrete. Here we know that the value of, here in table 20 we have 19, we have to be very careful Because if we look at this beam, which we have detailed so far, is that we are bending up two bars of 20 diameter at a distance of 1.96 from the center of the beam, and the critical section for shear is at 2.25 meters from the center of the beam. So when we are talking about this point where we are uh, considering the critical section, only 4 bars of 25 diameters are existing. So when we are calculating this design shear strength of concrete from table 19, we have to calculate it. The percentage has to be calculated corresponding to the area of steel present at this point of critical section. So this point is the main. So this AST1 here will be equal to AST1 will be equal to 4 into pi by 4 into 25 square, that is corresponding to the 425 diameter bars present at this critical section for shear. This is 1963.495 millimeter square. So P will be equal to 100 into AST upon BT, substituting these values, a value of P equal to 0.77. So if we look at this table, we have a value of 0.75 and 1, and the corresponding value of tau c for M20 is 0.56 and 0.62. If we are running out of time, so we can just round, we can use the value of 0.75 directly, because 0.77 is very close to 0.75. And we can use the value of tau c equal to 0.56. However, just for the sake of understanding, we will be solving this for the value of 0.77. So I can write, interpolating this value, 0.62 minus 0.56 divided by 1 minus 0.75, which will be equal to tau c minus 0.56 divided by 0.77 minus 0.75. So this gives us a value of tau c is equal to 0.5648 Newton per millimeter square. Because 0.56 and 0.5648 are very close, that is why I told you that you can simply, if you're running out of time, you can skip this step and use the value corresponding to 0.75%. So now, what is the design shear stress? Design shear stress is denoted by tau US. This is the shear stress which is beyond the value of the shear stress resisted by concrete. So the nominal shear stress acting on the beam was 0.775 Newton per millimeter square, and the one that can be resisted by concrete is 0.5648. So the difference between the two is equal to the design shear stress. So substituting these values, we obtain the design shear stress equal to 0.2102 Newton per millimeter square. So we can simply write tau US is equal to 0.21 Newton per millimeter square. So moving on with this value, we can calculate the shear force for shear reinforcement. This means that because this value of shear stress is not being resisted by concrete, so for this excess value we will have to provide shear reinforcement. So this shear reinforcement can be calculated is equal to VUS is equal to tau US into BD. Substituting the values, we get VUS is equal to 53655 Newton. So this is the value of shear stress to shear force to be resisted by shear reinforcement. So we will be providing shear reinforcement corresponding to this value of shear force. Now remember that we have to bend up to 20 diameter bars. So from clause 40.4c, for single bar or single group of parallel bars all bent up at the same cross section. So same cross section means that if you can see, we are bending up both the bars at this cross section. There might be cases where we bend them up at different cross sections, which is a discussion for another time. But for this case, we are bending up both the bars at the same cross section. So the value of VUS is given by this clause as 0.87 F by ASV sine alpha. So this simply means that the shear force which will be resisted by the bent up bars. This can be written as BUS dash also. So this is given by this formula where ASV will be equal to the area of the bars being bent up. So that is 2 into pi by 4 into 20 square. This calculates to be equal to 628.318 mm square. Now sine alpha, the code says alpha is the angle between the inclined stirrup or bent up bar and the axis of the member, not less than 45 degrees. So this is the axis of the member and this is the inclined stirrup. So this angle which it says is known as alpha and this cannot be greater than 45 degrees. So for simplicity we assume that alpha is equal to 45 degrees. Substituting the values to obtain VUS dash bent up, we get 160,410.2885 Newton. So this is the maximum value of shear resistance that can be provided from the bent up bars. However, the same clause 40.4 also mentions that where bent up bars are provided, their contribution towards shear resistance shall not be more than half that of the total shear reinforcement. So what does this mean is that the maximum value of shear resistance that can be provided from bent up bars is the total shear resistance to be provided by reinforcement, which we calculated in the previous slide. Here the total shear reinforcement shear resistance required by reinforcement divided by 2. So this value calculates to be equal to 26827.5. Now, when we calculated the value of shear reinforcement provided by bent up bars using this clause 40.4c, we obtained a value of 160410. This value is much greater than this maximum value permitted by the code. So, because this value is much lower, we will be considering this value for the shear reinforcement shear resistance provided by bent up bars. Let's say this value was lesser, this value was around 20,000, then we would have taken this value into consideration. Now because we can only provide half of the shear reinforcement in form of bent up bars, this means that whenever we provide bent up bars we have to provide stirrups as well. So to provide whenever we to provide stirrups along with bent up bars, what we have to do is that the total shear reinforcement or the shear force that was required to be resisted by reinforcement was 53,655 Newton, out of which bent up bars provided a value of 26827. For ease, I am ignoring the 0.5. So now the remaining value of shear resistance has to be provided by the stirrups. So the stirrups will have to provide the value of VUS minus VUS bent up. So the remaining shear force, which calculates to be equal to 26828 Newton. So this is the remaining value. Now what we have to do is we can simply design the stirrups corresponding to this shear force. So let us provide 10 mm diameter two-legged vertical stirrups for the remaining shear force. From clause 40.4, we have VUS for vertical stirrups is equal to 0.87 Fy ASVD upon SV. So if we look at this formula, we know the value of shear force which we have to resist using the vertical stirrups. We can calculate ASV corresponding to 10 mm diameter bars. D is the effective depth. So what we don't know is SV. So arranging this formula, we obtain 0.87 Fy ASV D upon VUS. So substituting the values, we obtain the spacing equal to 1543 millimeters. So the spacing required for 10 mm 10 mm diameter two-legged vertical stirrups is 1543 mm. However, as per clause 26.5.1, there is a minimum shear reinforcement which we have to provide using this formula. ASV upon BSV should be greater than equal to 0.4 upon 0.87 Fy. From this formula, we can calculate the minimum value of SV and the maximum value of SV and the minimum value of ASV. So the maximum spacing can be calculated using this formula. So rearranging, we get 0.4b upon ASV upon into 0.87 Fy. So substituting these values, we obtain SV max is equal to 405 mm from this formula. However, clause 26.5.1.5 gives us a maximum spacing of shear reinforcement, and it says that the value of maximum spacing can either be equal to 0.75d or 300 mm, whichever is minimum. So calculating 0.75d, we obtain 548 mm. So now out of 405 mm, 548 mm and 300 mm, we have to select the least value. So the least value is 300 mm. Therefore, we will be providing 10 mm diameter two-legged stirrups at 300 mm center to center, in addition to the two benta bars which we have provided. Now we will check for deflection as per clause 23.2 of the IS code, which gives us figure 4. Figure 4 simply asks us to calculate the percentage of steel, because maximum deflection occurs at the center of the beam. So here we will be taking the entire AST which we have provided, which is approximately equal to 2592 mm square at the center, and B is equal to 350 mm, D is equal to 730 mm. So this calculates to be equal to 1.01%. So if you see from figure 4, 1.01% will lie is approximately equal to 1%, and this line is the corresponding line which we have to consider for 1% or 1%. Now these lines are Fs, which can again be calculated from the formula given in figure 4. Fs is equal to 0.58 F by area of cross section of steel required upon area of cross section of steel provided. So we have calculated the value of required AST and provided AST in the previous slide. So substituting the values here for Fs, we obtain Fs is equal to 233.3 Newton per mm square. So now 233.3, this value will lie somewhere Fs between 240 and 190. So let's say that this is the value which is there. Now because we have to calculate the value from the figure corresponding to the figure, we can see that this 1% value and 233 coincide somewhere here. So this is almost equal to 1, the value of 1, or we can simply use the value of the modification factor for tension reinforcement from figure 4 KT, which we are actually calculating from this figure, is 1.05. You can simply take 1 also. I'm just taking 1.05 because I know that this will be slightly above the line of 240. 233 will be slightly above the line of 240. So I have just taken it equal to 1.05. You can take it equal to 1 as well. So now we can see from figure 4 that the value of MF, the modification factor for tension reinforcement, is equal to 1.05 or simply 1. From other figures, we can see that for compression reinforcement, because we have not provided any compression reinforcement, Kc will be equal to 1, and for uh, since the beam is a rectangular beam, there will be no modification factor for flange in T-beam. So Kf will also be equal to 1. Now we know that this is the formula for deflection, where 20 we achieve this value of 20 from clause 23.2.1, where it says that for simply supported beams for span less than 10 meters, the value is equal to 20. The deflection factor is equal to 20. So substituting these values in this formula, we obtain L by D max is equal to 21. Even if you consider this value equal to 1, we would have obtained this value equal to 20. Now what we have to calculate is L by D provided. What is the value of L by D that we have provided in this beam? L is equal to 6750 millimeters effective length and D is equal to 730. So this ratio computes to be equal to 9.2, which is much less than the maximum value of 21 which is permitted, and hence it is okay. So our beam has passed in the check for deflection as well. The next step is to provide the side face reinforcement because the depth of the beam is greater than 750 mm. I mean the overall depth of the beam is greater than 750 mm because our depth is equal to 800 mm. So we will have to provide side face reinforcement pertaining to clause 26.5.1.3. So it says that the area of the side face reinforcement ASS, if we call it, is equal to 0.1% of the web area. Web area is equal to B into D because it is a rectangular beam, and for percentage we dividing it by 100. So this calculates to be equal to 280 mm square. So we have to provide side face reinforcement equivalent to 280 mm square. So let's try two 12 mm diameter bars on each face. And this is also an important point that we have to provide this reinforcement along both the faces. We cannot just provide it on one face, we have to provide it equally on both the faces. So we are providing two 12 mm diameter bars on each face. So this computes to 2 plus 2 for both the faces into pi by 4 12 square, which computes to be equal to 452 mm square, which is greater than the value required for side face reinforcement. The spacing of the bars between of the side face reinforcement should be not greater than 300 mm. So we are providing a spacing of 300 mm center to center. So we have provided two 12 mm diameter bars on each face at a spacing of 300 mm center to center. So finally, this is the detailing of the beam where you can see the side face reinforcement. We are providing two 12 mm diameter anchor bars at the compression side. Then we have provided four 25 mm diameter bars and extended them into the support. Then two 20 mm diameter bars were also provided and were bent up at 1.96 meters from the center of the beam and have been extended into the upper support. These are the two cross sections at the center of the beam where you can see both all the 6 bars, and this is the cross section at the face of the support where we can see just the 4 25 mm diameter bars, and here you can see the bent up bars which have been transported to the upper end. So these are those bent up bars which are represented here. So I hope this lecture was clear to you. In this lecture, we covered a numerical problem based on design of simply supported beam where we have covered how to provide bent up bars. Thank you and have a nice day.
Alright, so welcome back to the Novatr. So we are having a design again with some complex stirrups and the reinforcements. So let's just model it in Revit. So as you can see that I do have column and our beam is resting on it. Okay, we are adding rebars into this beam. I have already set up the views. Okay, this is the plan view. These are the sections. So let's just understand the drawing first. So as you can see that it's divided into two parts, section at midspan and section at support. Okay, and all the annotations are done which will help us understand the drawing better. The span is 6 meter. So I have modeled that way only. Okay, 6 meter span. Okay, and I have created the views as well, middle, corner, and the elevation. Okay, so let's just start with the stirrup, that is our D. Okay, and D is this, and which is nothing but 10 mm, 2 leg stirrup, 300 mm center to center. So I'll go to the corner view. Okay, so I'll go to the structure. First I'll set the cover, and that is 20 mm. So under reinforcement cover, I select the element for which I am just setting up the cover, 20. Then rebar, and we have our stirrup here, 10 mm, 2 leg, and the spacing will be under rebar set, 300 mm. Just place it. Okay, now if you see, here it is. I'll make it fine. Okay, our first step is done. Now I'll add the rebars for this E, right, the corner ones, and will model rebar for C as well, because it's same. So if you see, it's 12 mm bar on each face, right, and E is also 12 mm anchor bars. Okay, so what I'll do, I'll go to rebar, we'll go with the typical shape, right, this one. First we'll set up the placement, which is perpendicular to the cover. We'll take the 12 mm. Okay, so we want this 3 bar, right, this 3 bar 12 mm, right. So what I'll do, to make it to equal distances, I'll just place it like this at this face. I'll select this and we'll go to the edit bars and we'll delete this one, remove bar, right. Now it's with the same distance, and I'll just mirror this. So I'll select this bar, so I'll go to modify and mirror draw axis, right. So I'll have this as well. Okay, it's done. Now it's time to model the G. Okay, that is this one, right, as you can see, that is our G. That's nothing but, let me just see the configuration, that is 25 mm space bar. Okay, at 1 mm center to center. To add the space bar, first I have to model this A, right, that's nothing but this, and that's 25 mm bar, the 4 bar 25 mm. So what I'll do, I'll again go to structure, rebar. Okay, we'll take the 25 mm and we'll place the rebar set with the maximum fixed number 4. It's done. Now it will be easy for us to model the space bar. So the same way, rebar, the typical shape, just change the orientation, the space, the placement, that is parallel to the work plane. Okay, and I'll place it. I'll make sure that is 20 mm space bar, 1 meter center to center. So I'll just place it. Okay, and we'll make it to the maximum spacing of 1 meter center to center. So if I just go to the elevation, right, so see, we have placed it. Now after placing this space bars, now it's time to add this B, right, that we have to edit it like this. Okay, so for that I'll go to the mid span, view that's here. I'll make it to fine. And what I'll do, I'll just copy this and we'll edit and remove this two bars and we'll make it to 20, right? So for that I'll create new 20 meter. I'll make it to 20 meter. mm. Okay, I'll just okay. So after doing it, I'll just go to the elevation view to adjust the bar. So as you can see that this is the bar that we have to edit, right? So for that I'll just take this, double click over it, and I'll just draw the shape. So let's see that up to how much we have to extend. So I'll extend up to this. Trim, TR is the shortcut, or else you can take from here as well under modify. And same way, I'll just mirror this. Let's just left. Yeah, and it's done. And I'll just click. Okay, so as per our requirement, the shape is done. So let's just see that how it looks to mid span and the okay, this is how it will look in mid and this is how it will look in corner, right? So this is how we can just model it. So I'll make it little bit easier to see, right? This is how we can model things in Revit. Thank you so much for watching.